Welcome to Emmanuele, Bobbio, as well as Mojgan, Hedayati.
Thank you. Thank you, and good afternoon, everyone. So I will start and then hand it over to Mojgan. Mojgan and I work for PJM in the Scenario Analysis and Special Studies group. The primary task of our group is to perform long-term planning, and capacity expansion modeling is a critical component of that. We have been reforming that process over the past year and doing some prototyping work with PLEXOS. There are two particular methodological aspects that we thought we would discuss with you today with regard to the modeling of policies, particular RPS constraints with their eligibility rules that states have, and then resource adequacy in the capacity expansion. So let's start with a brief overview of the agenda for this talk. First, I'm going to, at a very high level, discuss conceptually these two modeling aspects, renewable portfolio standards, particular eligibility rules, and modeling of resource adequacy that here we are doing by approximating ELCC relationships directly in PLEXOS, informed by a pre-processing of data using PJM official ELCC, that is accreditation process. Then I will hand it over to Mojgan, who will talk about, who will present a simple implementation of this concept with an east-west example of the PJM system, results and next steps. So first of all, the modeling of renewable portfolio standards. So of course, policies are a major driver of the energy transition. One aspect of the policies in PJM, but also in other areas of the US, is that they take the form of RPS mandates, and that these RPS mandates, they have rules regarding what sort of technologies are available and their location very often. So in this example, we are assuming that we have this RPS target that increases from 5% to 20% between 2029 and 2039 in the western part of the PJM system. And similarly, in the east, we have also an RPS target that goes from 10% in 29 up to 30% in 2039 in the east. Differently than for the west, where it's an undifferentiated demand for renewable energy, in the east, we are imagining here that there are eligibility rules, and particularly 1/3 of the target needs to be met with solar energy produced by facilities that are in the west, in the east, so not in the west. And for the remaining 2/3 of the target, if those remaining 2/3 of the target are met with solar, then that solar must be located in New Jersey, in the east. But if instead it's onshore wind, that onshore wind can be located anywhere. Could be in the east, but could also be in the west. Now, the way we are modeling this constraint in PLEXOS is essentially by imagining a supply-demand system, which essentially mirrors the trading of RECs in the real-world counterpart. So we have, and these constraints are represented for 2039, which is the terminal year of this expansion, in the table at the bottom of the slide. So we have the first constraint on the left of this table. That is sort of a market-clearing constraint, RTO-wide, that requires that the amount of demand for a REC produced by a particular technology type must be equal to the supply, so the generation of that technology type across the RTO footprint. And then we have the West component of that demand. We said that in the West, we need to have 20% of energy that is backed by renewable energy credits. Those renewable energy credits can come from anywhere and can come either from solar or from onshore. So demand, so basically there will be a demand for solar racks or for onshore rack, but the sum of these two demand components from the west must be greater than the 20% of the load from the west. And then regarding the east, we have a similar constraint on the right-hand side of the table, the top row. But then we have these two eligibility carve-out. And the first one is the solar carve-out, that is at least 1/3 of that 30%, so 10% of the load must be backed by racks that are from solar and from solar that is located in New Jersey. And additionally, for the remaining portion, what we require is that the remaining portion, if it's met with solar, then that solar must be in the east. And that's the final constraint. And the way that is expressed is that the generation of solar in the east must be greater than the demand for racks in the east for solar. And taken together, these constraints ensure that we don't need to second guess the way the policies will be achieved. We can just express the eligibility rules as they are written in the law, and then let PLEXOS determine what is the most economic way of achieving those policy targets. Then with regard to resource adequacy, what we do is, resource adequacy is very important. Well, it's very important as an objective when planning, but we see also that it is very important in the expansion that we get. This is well known, and Mojgan will present through this simple example what the impact of this resource adequacy constraint is. Here, the way we are doing it is rather than simulating multiple weather profiles in our capacity expansion, what we are doing is that we are actually relying on the PJM accreditation machinery, that is a Monte Carlo simulations based on historical data of weather and how units perform under those weather conditions, the load, in order to preserve the correlation of all those variables. What we do is that using that machinery, we run the ELCC code on a variety of portfolios, and we construct a surface. That surface captures the complementarity between the different technologies, storage, solar, and wind. And then what we want to do is that we want to take this surface and approximate that surface in PLEXOS, so that in the capacity expansion, rather than simulating that weather through a simple constraint, which can be interpreted as a capacity market constraint, we can enforce a resource mix that is actually resource adequacy from the perspective of the true accreditation process of PJM. The advantage of this approach is twofold. One is that really we obtain a capacity expansion which is actually consistent with what we do and with the true market incentives that are present in our capacity market. Another advantage is that we have an approach that is computationally cheap, because we don't need to simulate all sorts of scenarios in our capacity expansion. Everything is sort of captured by this very simple linear constraints. So right now, the way we are doing it in practice is that we are taking this surface and assume unidimensional curves. So for example, for wind, we will assume that the more you install a wind, the more the ELCC for wind drops. There is the complementarity with battery, right? So we know that the more battery we have in the system, the higher the LCC of wind is, other things equal. And the way we capture this is by having multiple curves, multiple of these unidimensional curves for wind that reflect the different penetration level of batteries that we can have in the system. At that point, we can run multiple simulations in parallel. Therefore, we are not increasing the time of the process. We can run all this sort of simulation in parallel, like a storm, if you want. And then once we get the result, we can run those resource mixes through our ELCC machinery, get the exposed true ELCC for that particular resource mix, and then just select the simulations out of the 10 or 20 that we ran that just has the better score. That is, that has an assumed ELCC curve that end up corresponding to the true ELCC for the resource mix that is selected by PLEXOS under that particular ELCC curve. So this is the approach. It's a starting point, but I think it's interesting and promising, and then Mojgan will discuss the results and then the next steps.
So in this part of the presentation, we are going to talk about an illustrative example. It's an East-West model, like simple two-node simplified model of PJM. The load is PJM's load forecast as of 2023, and we are starting the simulation in 2029, so our starting position in terms of resource fleet is our existing generation plus what we have in the generation queue that's going to make the cut to be included in our RTEP five-year out case. In terms of build cost or capital cost, we are using the numbers from S&P, their spring 2023 release. And we are adjusting those with adjustment factors from NREL's annual energy outlook to adjust for different regions. For fuel price, we are using the fuel price forecast from Hitachi. The policy retirements are the thermal retirements based on PJM's internal assessment of different states' policies. And the numbers that we have used here are consistent with PJM's 4R report that was published in 2023. That's resource retirement, replacement, and risk. And for RPS policies, those are what Emmanuele presented a few slides ago. So we have different eligibility rules for different areas. And here we are showing the results. We are looking at the generation mix in 2032. And what we are looking for here is the impact of modeling those ELCC-based resource adequacy constraints. And on the left, what we have is how would our generation mix look like in 2032 if we didn't model any resource adequacy constraint. And on the right, we are seeing how it will look like if we are modeling the resource adequacy constraint. So when we are not modeling any ELCC-based resource adequacy, what is driving our build is basically the load balance constraint. And because our peak load is happening during the summer, and because the cheapest resource that we have in the resource mix candidate is solar, we are going to build solar with some battery storage to be able to handle those few hours after the sun has gone down and we still have a high load. And that's basically our mix. Now, if you take that mix and you talk to anyone in the operation in PJM, they will tell you that the resource adequacy problem is not a problem of being able to serve the load during the summer peak hour. It's the problem of being able to serve the load during a winter storm when you have thermal outages and your solar is not performing well. So now what happens is when you model the ELCC-based resource adequacy constraint, you will see that those winter risks are going to impact your build. So we are building more wind along with more storage to be able to handle that. And now the bigger picture is maybe you do not need to have an 87, 60 hour for all years to be able to come up with a solution for your build. Maybe this two simple constraints, seasonal ELCC that you have for winter and summer is going to be enough to direct your build to be able to address your winter risk. All right, so in terms of next steps, what we're thinking about is implementing a multidimensional ELCC-based resource adequacy constraint. And that means that so far, whatever we have been doing has been unidimensional, meaning that the ELCC of solar is depending on solar penetration. The ELCC of wind only depends on wind penetration. But the reality is your firm capacity is going to be dependent on your solar penetration, wind penetration, the penetration of battery, and so on. And if we are able to model that, then first you're going to get more accurate results. And then also you're going to have a better, superior computational version of this, because the way we are calculating the ELCC is based on Monte Carlo simulation upfront. So you are shifting all the computation burden to upfront to come up with those numbers, and then use those numbers as simple linear constraints, resource adequacy constraints in the model. I'll just wrap up with saying that these resource adequacy concerns are very important in our generation expansion builds, not only because they are showing the reliability needs of the system, but in terms of the fact that they are going to translate those reliability needs into economic incentives in terms of capacity market and how you're accredating those resources in the capacity market. Yes, this is our last slide. Yeah, with that, we'll be happy to answer any questions.
Hi, a question, Wade Schaefer with Exelon. You may have said this in the beginning, and following along, I may have lost it, but where are you doing the ELCC modeling? I realize it's a separate, like, exogenous process outside the PLEXOS, the capacity expansion. Are you using PLEXOS to do the ELCC modeling too, or what are you using to calculate the ELCC values and plug in the PLEXOS?
Yeah, so basically, PJM has its own ELCC machinery, and that's our resource adequacy team. So they have different weather scenarios that they model to come up, like thousands of different weather scenarios. And that's a Monte Carlo simulation that they run through to come up with those numbers.
Daniel from RWE. Can you comment on, so because you show ELCC and the relationship between ELCC of batteries and wind, that means you're taking into account like post-dispatch ELCC, right? Like curtailment and things like that. So can you comment on the sort of the impact and the relevance of taking into account the curtailment into the ELCC? You could take the ELCC as, you know, before curtailment or after curtailment, yeah. And if you see big impacts on doing that or not.
Yeah, so here what we are doing, as Mojgan was saying, is to use the actual accreditation process. The way that process works is that, okay, so the way that process works is that, first of all, we look at the historical weather, and then that historical weather is binned, and then conditional on drawing a particular bin, we will have within that particular weather bin an associated load and outages and renewable performance. So then we bootstrap all that data all at once, and that allows to maintain the correlation between the realizations of those variables. Then once you get these draws, then what you do, what the algorithm does is that it simulates the system under perfect dispatch, and then under that perfect dispatch determines the hours when there's just not enough generation to meet the load. Those are the hours when you have a critical time, and those are the hours in which you measure the performance of resources, and that is, in turn, it's going to be the ELCC then of the particular technology class. So And that simulation is actually done not only under perfect dispatch, but assuming that there are no transmission constraints. So there are not going to be curtailments due to transmission limitations, but in that simulations, you can have curtailments due to too much generation relatively to the load, but it's just a nuisance in that particular simulation given the goal of just measuring resource adequacy. And with regard to the ex ante and ex post, so what we do ex ante is that the way you can think about it is populating a table of ELCC values given resource mixes. Then we run the capacity expansion, and then the ex post validation is done by rerunning again for that particular resource mix the true ELCC machinery and checking that the ex post results are actually equal to the ex ante ELCC curve that you use to produce that particular expansion. Now, this validation process is time-consuming and computationally demanding, but that is what, with this last extension that Mojgan was discussing, that is moving to the multidimensional ELCC curve directly being represented within PLEXOS, that is the step that would be eliminating. So it's true that upfront maybe you need to calculate the ELCC for, I don't know, 200 portfolios, but then you form the surface and you can generate all of the scenarios you want without need to do any sort of additional ELCC work.
How do you account for different durations of energy storage in your ELCC methodology?
So the way we do that is because we have, so the way we are doing it now, when we will have this multidimensional surface directly implemented in PLEXOS, then that will be directly captured in the expansion. The way we are doing it now is, in the figure we had these three curves, low, medium, and high, right? So we had these declining profiles, that is the relationship between the ELCC of wind and the penetration of wind, right? But then we have three curves. One is under the assumption of high battery penetration, medium battery penetration, low battery penetration. And then you run these three different simulations of PLEXOS in parallel, and they will deliver different portfolio mixes because they're assuming different ELCC curves. But then you can run your ELCC code again on those three different results, those three different resource mixes, and see which one performs the best in the sense that the ex post ELCC is actually equal to the ex ante ELCC. And of course, I mean, we are using the PJM ELCC machinery, but you can use the PLEXOS ELCC machinery or whatever algorithm you have to compute the ELCC.
Hello. Hey, Jimmy Nelson from E3, and I'm excited to see you're interested in an ELCC surface in PLEXOS. I think we've done 2 ELCC surfaces for 2 of our clients, and while it's possible to do in PLEXOS, I wouldn't say it's the easiest thing. So I'm wondering if you have a kind of a path forward for how you think you plan to implement it. Yeah, we used custom constraints quite a lot, but yeah, what's your kind of implementation plan if you've gotten that far?
Yeah, so the unidimensional curves we have implemented, and that is fully implemented. And similarly for also the policy constraint, that's something that I forgot to mention. Related to the policy constraint, 2 aspects that I want to emphasize is that this is a simple example, but actually the same logic, we used it to successfully model all of the policy constraints in PJM. So it's simple, but it's actually quite powerful. The second is that from those constraints, you get also the shadow prices that gives you, decompose the cost of the different components of the policy and say how much is this particular eligibility rule costing to the policymaker. That's also something that you get, which is important, I think. In terms of the ELCC, the part that we will need to implement is this multidimensional surface, and for this, we're actually working with Energy Exemplar to see how that could be done. We propose it at the hackathon. I believe Energy Exemplar has already worked and perhaps solved that problem. So hopefully it will come soon.
Any other questions? No. There we go.
Hi, thank you. Just confirming the battery assumptions are for 4-hour batteries, or is it multiple durations?
It's 4 hours.
It's 4 hours.
It's 4 hours.
Thank you.
That's a good question. And yeah, and I think that more generally, this is a high level, if you want, methodological approach. But then, of course, one could have other technologies. And experimenting with other technologies, long duration storage, hydrogen, and so on, that could be important, yes.